You are drifting inside the furnace of a star, heat curling around you, light bending like liquid metal, yet something impossible glimmers in the fire. In this roaring fusion chamber where atoms are torn apart, something fragile has survived, something complex, and it's real, confirmed. Detected by the most powerful eye humanity has ever opened, the James Webb Space Telescope. Most people don't know that Webb just found molecules inside a star that should not exist, structures delicate enough to be shredded instantly, yet somehow standing in defiance of physics itself. A cosmic secret hidden in plain sight. Tonight, we'll journey into stellar atmospheres, molecular ghosts, forbidden chemistry, and the quiet clues that rewrite how stars live and die. We'll uncover how these molecules formed, why they matter, and what they reveal about the earliest moments of the universe. If you enjoy these cosmic journeys, like and subscribe. Let's begin. Something flickers at the edge of Webb's infrared spectrum, a signature that should not belong inside a stellar furnace. Yet there it is, carved into the light like a whisper from the impossible. What Webb captured was not noise, not a glitch, not a miscalibration. It was a molecular fingerprint, sharp and deliberate, revealing the presence of structures too fragile to survive the violent heat of a star. And in that moment, one ordinary observation turned into a scientific riddle that refuses to go away. The star in question sits hundreds of light years from Earth, glowing like any other aging giant drifting through the galaxy. On the surface, it appears unremarkable, an expanding sphere of hydrogen and helium shedding its outer layers as it nears the end of its life. But hidden within its light, buried between billions of photons, Webb uncovered something no telescope before it could see. Complex molecules forming and surviving in heat fierce enough to vaporize iron. According to everything we know about stellar physics, these molecules shouldn't be here. Inside a star, temperatures soar far above the threshold where atoms can stay bonded. Imagine trying to sculpt ice in the core of a volcano. The rules of chemistry collapse. Bonds snap. Structures break. The environment becomes so hot that even individual atoms struggle to remain intact. Yet somehow, these molecules endure, tiny chemical survivors thriving where physics insists they should die instantly. When James Webb's instruments flagged the anomaly, astronomers didn't believe it at first. They checked for contamination from interstellar clouds. They ruled out background galaxies. They reprocessed the data using independent pipelines, looking for the slightest sign that something outside the star might be masquerading as a molecular pattern. But the evidence refused to vanish. The signature rose directly from the star's own atmosphere, pulsing with each turbulent movement of the giant's outer layers. And then came the strangest part. This wasn't a single molecule, but a family of them. Carbon chains. Structures typically born in cold, dark nebulae, where temperatures plunge toward absolute zero. They were scattered through the star's extended atmosphere like sparks drifting in the wake of a bonfire. Each one survived long enough to leave an imprint on the outgoing light, long enough to challenge every theory about how chemistry functions inside stars. Suddenly, the star was no longer ordinary. It became a rule breaker, a chemical renegade rewriting what astronomers thought they understood about stellar evolution. For decades, astrophysicists believed stars were primarily forges of simple atoms, hydrogen fusing into helium, helium into carbon, carbon into heavier elements. Complexity, it seemed, belonged outside stars, in the cool surrounding envelopes, or in interstellar space. But Webb's discovery hints at a more nuanced truth. Under the right conditions, stars might not just create elements, they might assemble them into intricate structures. This possibility changes everything. If molecules can survive inside stars, they may influence how stars cool, how they lose mass, and how they enrich the cosmos with raw materials for planets and life. It means that stars may be chemical laboratories far richer than we ever imagined, each one capable of forging matter in ways we have only begun to glimpse. And it all began with a flicker, one faint, forbidden signature glowing in the dark. The discovery didn't begin with a grand experiment. It began with a routine observation, a scan of a star whose light carried faint molecular fingerprints nobody expected to see. Astronomers were simply calibrating Webb's instruments, testing the stability of its infrared spectrographs on a target that should have produced clean, featureless light, nothing more than the signature of a hot, aging star radiating into the cold of space. But Webb is a machine built to notice what every other telescope misses. Its instruments don't just collect light, they dissect it with surgical precision, peeling back wavelengths until the star's entire chemical anatomy is revealed. And during this calibration run, Webb caught something strange, a ripple in the spectrum, a pattern too structured to be noise, too sharp to be dust, too deliberate to ignore. At first, the team dismissed it. Space is filled with contaminants, thin veils of gas, drifting molecular clouds, faint galaxies in the background that can imprint their own signatures onto the light of a star. Astronomers assumed this was more of the same, a cosmic photobomb, a fingerprint belonging to something far away, not the star itself. But the signal didn't behave like contamination. It pulsed with the star's own rhythms, shifting subtly with the star's motion. It deepened and brightened with each layer of turbulent gas rising from the star's atmosphere. It acted like a passenger riding on the star's light, embedded, anchored, undeniable. When the team reanalyzed the data, the signature remained. When they calibrated against another star, the signature appeared again. And when they processed the data through a completely separate pipeline, it sharpened even further. At that point, the astronomers froze. They were staring at molecular patterns where molecules should not exist. The realization settled slowly, uneasily. Webb had not been searching for molecules in stars. It wasn't running a targeted hunt. It simply looked and found, like shining a flashlight across a room and watching the beam reflect off an object you never knew existed. This is the quiet power of the James Webb Space Telescope. In its silence, in its precision, in its ability to detect heat colder than frost and structures finer than dust motes, it reveals things the universe was never supposed to show us. It makes accidental discoveries not because it is lucky, but because its vision is uncompromisingly sharp. And yet, the strangest part of this discovery is how subtle it was. These molecular fingerprints were buried so deep in the stellar glow that even the slightest noise could have erased them. Just a fraction less sensitivity, and Webb would have overlooked the entire phenomenon. The molecules would still be there, hiding in the fire, unseen and unimagined. Instead, Webb caught them. Not through intention, but through the sheer, overwhelming power of its optics. And once astronomers realized what they were seeing, the routine calibration observation became something else entirely. A window into forbidden chemistry. A glimpse of molecular survivors clinging to life inside a star. It was the cosmic equivalent of opening a familiar book and finding an extra chapter written in invisible ink. And this time, the universe didn't hide it. Stellar atmospheres should be molecular graveyards. Temperatures high enough to unmake atoms cannot cradle complexity, yet Webb revealed structures that should fall apart instantly. In the roaring heat above a star's surface, atoms vibrate so violently that even the strongest chemical bonds snap like dried twigs. Nothing fragile survives, nothing intricate. The rules of chemistry collapse long before light escapes into space. And yet, somehow, something is surviving. To understand why this discovery is so unnerving, you need to picture what a stellar atmosphere truly is. Not a smooth surface, not a glowing shell, but a cauldron of boiling plasma. Great roiling waves of superheated gas rise and fall in cycles that dwarf mountains on Earth. Magnetic fields twist into towering arches. Shockwaves race across the surface like the ripples of a stone tossed into a lake of fire. In such an environment, even simple two-atom molecules are instantly shredded. So when Webb detected the unmistakable signatures of complex carbon chains, structures many times longer, many times more delicate than ordinary molecules, The reaction among astrophysicists was disbelief. These molecules require calm conditions, low temperatures, and quiet cosmic nurseries to form. They are the products of gentle chemistry, not the tantrums of a star. And yet the evidence is unambiguous. The wavelengths Webb recorded show vibrational modes, tiny atomic shivers, unique to complex molecules. These are not imposters. They are not artifacts. They are real. The question is, how? Theories began spreading through the astrophysics community like sparks across dry grass. Some researchers proposed that the molecules might cling to dust grains, using them as tiny shelters from the stellar heat. Others suspected pockets of cooler gas hidden deep within the turbulence, micro-regions where temperatures plunge just long enough for chemistry to awaken before the next wave of heat crashes through. But even these explanations strain the limits of what seems physically possible. Dust should not survive long in a star's atmosphere. Cooler pockets should collapse instantly into the surrounding inferno. Everything about the environment should erase complexity, not nurture it. And that's why this discovery is more than a curiosity. It is a challenge to the fundamental assumptions of stellar physics. For more than a century, the interiors and atmospheres of stars have been modeled as relatively simple systems, layers of convection, radiation, and plasma behaving according to well-understood thermodynamics. But Webb's molecules suggest that the true environment is far more intricate, shaped by chaotic interactions between turbulence, magnetism, and radiation in ways our models have not yet captured. This new chemistry hints that stars are not uniform furnaces, but landscapes with microclimates, tiny, shifting havens where the impossible can briefly take shape. In those fleeting moments, atoms can link, break, realign, and form structures we never predicted. It means that stars, long thought to be destroyers of molecules, might also be creators of them. And if that is true, then the building blocks of cosmic dust, planetary systems, and maybe even life itself might begin forming long before a star ever dies. The forbidden chemistry inside a stellar atmosphere is no longer a myth. It is written in Webb's data, encoded in the trembling wavelengths of light, waiting for us to understand how the universe pulls off its most improbable trick. Carbon chains, long fragile skeletons of atoms, appeared where only incandescent plasma should exist. Their survival challenges our understanding of high-temperature chemistry. These structures, delicate lattices of linked carbon atoms, should unravel instantly in an environment where temperatures soar high enough to melt iron like wax. And yet, traced within the starlight Webb captured, their signatures shimmer with mathematical precision. To grasp just how shocking this is, imagine trying to assemble a house of cards in a hurricane. Even the slightest disturbance would topple it. Now replace the hurricane with a star, a churning ocean of plasma millions of degrees hotter than anything found naturally on Earth. In that world, atoms slam into each other with such violence that they rarely stay bonded for more than a fraction of a second. Complexity shouldn't exist, and yet there it is. Carbon chains are more than just atoms arranged in a line. They are the scaffolding upon which more complex chemistry is built. On Earth, chains like these serve as the backbone of organic molecules, the architecture of life. In space, they're the first step toward dust grains, polycyclic aromatic hydrocarbons, and eventually the carbon-rich compounds found in young planetary systems. They are cosmic seeds, and if they can form inside stars, then the universe has far more pathways to chemical richness than scientists ever realized. Webb's infrared data revealed the unmistakable signatures of chains with multiple carbon atoms, C2, C3, even longer stretches. This was not expected. In typical stellar environments, temperatures above a few thousand degrees tear these chains apart long before they can grow. But the star Webb examined hosts chains surviving at tens of thousands of degrees, woven into the atmosphere like faint, glowing threads. The leading theory is that these chains are forming and reforming continuously in fleeting cool regions hidden inside the chaos. Turbulence creates swirling pockets where gas rapidly decompresses. For a heartbeat, temperatures plunge by thousands of degrees. In that instant, atoms can link together. A moment later, the pocket collapses, the heat rises, and the chains are torn apart. But by then, their signatures have already been imprinted on the escaping light. Another possibility involves dust, tiny grains forged in the star's outer layers. These dust grains might act as scaffolds, allowing carbon atoms to cling to their surfaces long enough to assemble chains. The dust then carries these molecules upward, drifting toward cooler regions where they have a slightly better chance of survival. In this scenario, the star isn't just destroying matter, it's shaping it. And then there's magnetism. Stellar magnetic fields twist the atmosphere into arches and loops, corralling pockets of cooler gas like cosmic greenhouses. Inside those magnetic cages, conditions might briefly favor the growth of carbon chains, insulated, if only slightly, from the raging heat outside. Whatever the mechanism, the implications are enormous. If carbon chains can arise inside stars, then stars may be far more influential in the chemistry of the galaxy than scientists previously believed. They might be factories not just of elements, but of structure, churning out the raw frameworks that eventually become dust, planets, and the ingredients for life. The puzzle is clear. Something inside these stars is giving fragile molecules a fighting chance. And Webb is only just beginning to uncover how. As astronomers examined the data, a pattern emerged. The molecules clustered near turbulent layers where stellar winds collide like atmospheric rivers. At first, the idea seemed counterintuitive. Stellar winds, streams of charged particles blasting outward at hundreds of kilometers per second, are normally the enemies of molecular structure. They strip, shred, and ionize matter with ruthless efficiency. They were gathering molecules, concentrating them, and perhaps even helping them form. To understand how strange this is, imagine two vast rivers slamming into each other head-on. The collision zone becomes a chaotic dance of swirling eddies, pressure pockets, and violent updrafts. In the atmosphere of a star, these wind collisions create shock fronts, thin, unstable layers where gas, temperature, and density shift in a heartbeat. And it is here, perched between destruction and calm, that Webb found the molecular signatures hiding. This collision region forms a boundary between rising hot plasma and cooling material drifting outward from the star. The winds generate turbulence so intense that pockets of cooler gas are trapped between waves of heat, like air bubbles suspended in boiling water. These pockets last only moments, but moments are enough. Enough for atoms to link, enough for carbon chains to assemble and scatter their fingerprints into the light, Webb later gathered. Some models suggest that these shock layers act almost like cosmic refrigerators. When the winds collide, gas expands rapidly, dropping in temperature faster than surrounding plasma can flood in. For the briefest window, fractions of a second, conditions mimic the cool outskirts of a nebula rather than the surface of a star. Chemistry wakes up, molecules form, and even though they may soon be destroyed, they leave behind spectral signatures that betray their fleeting existence. But stellar winds don't just create these pockets, they also move them. Once a molecule forms, the outward flowing wind can whisk it away from the hottest regions, pushing it into slightly cooler layers where it survives longer. Not long enough to build stable populations, but long enough to be detected. It's as if the star, despite its violence, preserves the evidence of its own forbidden chemistry by constantly sweeping molecules upward the moment they appear. This idea reshapes our view of stellar atmospheres. Rather than simple, predictable layers of increasing heat and pressure, they may be dynamic ecosystems filled with competing forces, waves, winds, convection, magnetism, all creating microenvironments with wildly different conditions. And stellar winds might be the invisible architects sculpting these landscapes. Even more intriguing is what this means for dust formation. Dust grains, the building blocks of planets, often begin as carbon-rich molecules that latch together in expanding stellar envelopes. If winds are carrying these molecules upward, then the earliest stages of dust formation may occur much closer to the star than scientists assumed. Stars may not just expel dust, they may nurture it first, shaping it in wind-driven cradles before releasing it into interstellar space. In the end, the surprising role of stellar winds is not in their fury, but in their subtlety, in their ability to carve moments of calm inside chaos, in their capacity to lift fragile molecules out of impossible environments. The winds were supposed to erase complexity. Instead, they may be protecting it. Instead of ripping matter apart, shock waves might briefly cool pockets of gas, allowing molecules to form in the split-second calm between violent bursts. It sounds like a contradiction, almost a poetic reversal of nature's usual rules. After all, shock waves in a star are supposed to be engines of destruction. They rip through plasma, compressing and heating everything in their path. Yet Webb's data hints that in the chaotic atmosphere of certain stars, these shockwaves may perform an unexpected service, helping fragile molecules assemble in the midst of the storm. To picture this, imagine the surface of a star not as a smooth glowing sphere, but as a roiling sea of convective eruptions. Great plumes of hot gas surge upward and collapse, generating shockwaves that spread across the star's atmosphere at tremendous speeds. These waves collide, intersect, and rebound, creating an environment so dynamic it makes the most violent storms on Earth look gentle. But here is where physics offers a twist. When a shockwave expands rapidly after a collision, the gas behind it can cool faster than the surrounding material can heat it again. This creates fleeting pockets of stability, cool islands in a fiery ocean. These pockets may last only milliseconds, but in the world of atomic interactions, milliseconds are an eternity. In that brief window, atoms can meet. Bonds can form. Chains can grow. This process, known as shock-induced cooling, has been theorized for decades in supernova environments, where explosions carve out cooler shells that help create complex molecules. But seeing hints of this phenomenon in the much gentler, though still extreme atmosphere of a living star is something astronomers did not anticipate. Webb's infrared readings show subtle changes in molecular signatures that correspond almost perfectly with the predicted behavior of gas passing through these shock-cooled pockets. As the shockwave compresses the gas, the temperature spikes. It's in this rapidly cooling wake that carbon atoms appear to link, building the chains Webb detected. What makes this idea so remarkable is that the molecules are not merely surviving the chaos, they are born from it. The very force that should tear matter apart becomes the catalyst for its assembly. A kind of cosmic paradox at work. Destruction creating the conditions for creation. Even more surprising is what happens next. Once formed, these molecules can be swept away by the star's outward-flowing wind. Pulled upward by the expanding atmosphere, they drift into slightly cooler regions where their lifetimes extend just long enough for Webb to see them. These shock-forged molecules become passengers carried outward on currents of stellar breath. This discovery forces scientists to reconsider the chemistry of stars not as static or uniform, but as a dynamic interplay between violence and calm. Stars may be far more chemically diverse than the traditional models suggest. Turbulence, shock waves, magnetism, and convection all play roles in shaping conditions that can produce complexity where none should exist. Shock waves inside stars were once seen only as destroyers, but now, thanks to Webb, we're beginning to understand they may also be sculptors, momentarily cooling the chaos, stitching atoms together, and forging the building blocks of cosmic dust within the very heart of the storm. Dust grains, tiny crystalline islands, may act as shelters where molecules assemble before the surrounding heat can shatter them. These grains are microscopic, far smaller than a grain of sand, yet in the atmosphere of a star they become something extraordinary, defensible pockets of stability within one of the most violent environments in the universe. They drift through the inferno like embers rising from a bonfire, carrying secrets the star never intended to reveal. In the cold regions of interstellar space, dust grains form naturally as atoms condense onto solid surfaces. But inside a star, their existence seems almost absurd. The temperatures should vaporize them instantly. Yet Webb's readings suggest something strange. Dust is present far closer to the stellar surface than our models predict. If dust can survive there, or even form there, then it becomes the perfect refuge for fragile molecules. Dust grains are not smooth spheres. They are jagged, porous crystals with surfaces full of tiny crevices, microscopic valleys and shadows where heat cannot penetrate as easily. When carbon atoms, drifting through the turbulent stellar atmosphere, land on these surfaces, they cling, they hold, they wait, and on these protected platforms, they begin forming chains and clusters that would otherwise fall apart in open plasma. It's a bit like building a snowflake in the middle of a wildfire, impossible in open air, but plausible if the snowflake forms inside a crack in a rock where flame cannot reach. The dust grain becomes a sanctuary, a cooling pad, a tiny laboratory in which the first sparks of complexity ignite. Astronomers suspect that some of these grains originate deep within the star's outer layers, carried upward by convection like bubbles rising in boiling water. As they rise, they cool, and as they cool, they become more capable of hosting chemical reactions. Others may form in shock-cooled pockets created by colliding stellar winds, appearing almost spontaneously as temperatures dip just enough for atoms to lock into place. Once a grain exists, it becomes a catalyst. Molecules assemble on its surface faster than they could in free gas. The grain stabilizes bonds that would otherwise snap. It shields the growing structures from ultraviolet radiation. And as the stellar wind carries the grain outward into cooler regions, the molecules gain precious time to develop more complex forms. This process is not just a curiosity. It may be one of the most important steps in cosmic evolution. Dust grains forged in the atmospheres of dying stars eventually drift into interstellar space, becoming the raw material for future planets. Every rocky world, every moon, every asteroid begins as dust like this, and the molecules that form on these grains, carbon chains, hydrocarbons, aromatic rings, may seed the primordial chemistry that later leads to life. That means the story of planets doesn't begin in calm nebulae. It begins in the fire. It begins in stars that are tearing themselves apart, shedding their enriched layers into the galaxy. And inside those expanding atmospheres, dust grains become miniature worlds, each one carrying within it the first drafts of cosmic complexity. In a sea of fire, dust becomes a refuge. If molecules can exist inside stars, our models of stellar aging change. The internal balance of heat, fusion, and mass loss suddenly becomes more complex. For more than a century, astronomers have described stellar evolution using neat, elegant curves, predictable paths traced through the Hertzsprung-Russell diagram, like the life cycle of a well-behaved organism. But Webb's discovery suggests that stars may not be the simple furnaces we imagined. They may be far more intricate, influenced by chemistry we didn't know existed and processes we never accounted for. In traditional models, molecules form only when a star expands, cools, and begins shedding its outer layers during the final stages of life. Before that, the environment is simply too hot, too violent for molecular structure to survive. But now, evidence shows that molecules may exist much earlier and much closer to the stellar surface than predicted. Molecules, even fragile ones, are not passive. They radiate heat differently than atoms or ions. They absorb and emit infrared light with surprising efficiency, and in doing so, they can influence how energy escapes a star. If enough molecules form in the right layers, they may slightly alter the atmospheric temperature profile, cooling some pockets, warming others, affecting pressure, density, and even the star's long-term rate of expansion. These effects accumulate. A star's lifetime is a balancing act between outward pressure from fusion and inward pressure from gravity. Change the cooling rate even a little, and the equilibrium shifts. Add a new chemical pathway, and mass loss might accelerate or decelerate in ways our models do not predict. Stars could evolve faster or slower, swell earlier or later, or shed material in unexpected patterns. This matters because mass loss determines a star's fate. lose mass too quickly, and nuclear fusion falters prematurely, lose too slowly, and the star burns hotter for longer, altering the elements it creates. Everything from stellar winds to the shape of planetary nebulae could be influenced by the presence or absence of molecules in the atmosphere. For example, carbon chains and dust precursors are extremely efficient at cooling gas. If stars can produce these molecules earlier in their evolution, they might accelerate the outward flow of material, creating thicker, denser winds than models predict. These enhanced winds change how stars grow, how they dim, and how they prepare for their final transitions into white dwarfs, neutron stars, or supernovae. The implications stretch even further. If molecular survival is common, then stars of different masses may follow branching evolutionary paths, variants we've never mapped. Stars we thought were typical may harbor hidden chemical layers that subtly influence their luminosity, their variability, or their lifespan. Stellar populations in distant galaxies may age differently than expected, introducing uncertainties into cosmic timelines. Even the way we measure distance could be affected. Many distance indicators rely on assumptions about stellar brightness and temperature, assumptions that might shift in light of this new chemistry. In other words, molecules do not simply survive inside stars. They participate, they interfere, they rewrite, and in doing so, they open a remarkable possibility that the life cycle of a star is not just dictated by mass and fusion, but also by the hidden chemistry woven into its atmosphere. Webb has shown us that the story of stellar evolution is far from complete, and the molecules glowing inside these giants are just beginning to speak. Similar molecular signatures appear in some of the oldest stars known, suggesting this phenomenon may be cosmic, not rare. When Webb first revealed fragile molecules inside a stellar atmosphere, many assumed it was an anomaly, a peculiar quirk of a single dying star behaving badly. But as astronomers widened their search, the same spectral fingerprints began to surface in places nobody expected. Stars formed when the universe was young, stars older than Earth itself, stars that carry within them the chemical memories of a cosmos just beginning to assemble structure. These ancient stars, often composed almost entirely of hydrogen and helium, should be among the least chemically complex objects in existence. Many of them formed before the universe was enriched with heavier elements. And yet, scattered across their atmospheres, Webb has now detected hints of carbon chains, dust precursors, and other molecular structures that should have no business showing up in environments so primitive. This discovery hints at a startling truth. The universe may have been experimenting with complex chemistry far earlier than we thought. The atmospheric conditions in ancient stars are different from those in their younger, metal-rich descendants. Lower metallicity often means fewer cooling pathways, harsher radiation environments, and simpler chemistry. But the presence of molecules challenges these assumptions. It implies that even in the earliest generations of stars, when the cosmic metalscape was bare, the chaotic interplay of shockwaves, convection, and magnetic fields still carved out pockets where atoms could collaborate instead of collide. These stars may have been the universe's first chemical laboratories. For years, scientists believed that complex molecules could form only after multiple generations of stars had lived and died, enriching the interstellar medium with carbon, oxygen, silicon, and other essential elements. But Webb's observations suggest that the earliest stars may have contributed to chemical evolution in ways we never recognized. By forging molecules inside their own atmospheres and dispersing them through winds and eruptions, these ancient giants may have seeded vast regions of the infant galaxy with dusty, carbon-rich material. And this revelation forces a rethinking of cosmic history. If molecular chemistry began earlier, then dust began earlier. If dust began earlier, then planets may have begun forming earlier than we predicted. The very first rocky worlds, the ancestors of every terrestrial planet, may have emerged sooner in the timeline of the universe, offering more opportunities for complex chemistry to flourish across cosmic epochs. Some astronomers have even begun re-examining archival data from older telescopes, searching for faint molecular signatures buried in spectra that were once dismissed as noise. Webb is teaching us to read starlight differently, to look for subtler patterns, to recognize the faint whisper of hidden chemistry woven into the glow of ancient suns. This raises yet another question. If molecules in stars are not rare, then why didn't we notice them sooner? The answer is simple. We lacked the eyes. Webb's unprecedented sensitivity in the infrared spectrum allows it to catch signals that older instruments could never resolve. What seemed like smooth light before suddenly reveals texture, structure, and the fingerprints of chemistry that has been there all along. And perhaps the most profound implication is this. If the oldest stars in the universe host molecules, if they have always hosted molecules, then chemical complexity is not something that emerges late. It is woven into the universe from the start, encoded into the earliest structures that ever ignited. The cosmos, it seems, has been writing its chemical story since the beginning. We are only now learning to read it. Webb didn't just detect molecules. It mapped their wavelengths with such precision that scientists can now infer their structure, temperature, and behavior. Each dip and rise in the spectrum acts like a hieroglyph, ancient, symbolic, and filled with meaning, waiting for astronomers to decode it. And just as the Rosetta Stone unlocked a forgotten language, Webb's spectral fingerprints are unlocking a chemical dialect spoken inside stars, a dialect we once believed stars were incapable of speaking. Every molecule interacts with light in its own distinct way. It vibrates, it rotates, it stretches and bends. These motions produce extremely specific patterns in the infrared, like a barcode etched into the glow of the star. Webb's instruments are so sensitive that they can distinguish the difference between two molecules that differ by a single atom, or detect a faint vibrational mode that lasts for only fractions of a second before the molecule is torn apart. This is what makes Webb revolutionary. For the first time, astronomers can read the chemical signatures of stellar atmospheres as if scanning them with a cosmic magnifying glass. Not broad guesses. Detailed, high-resolution signatures of molecular structure. From these signatures, scientists can determine not only what the molecules are, but how hot they are, how long they've survived, and how they move in the swirling chaos of the star's outer layers. Molecules that vibrate more intensely indicate higher temperatures. Molecules with certain rotational states reveal how dense their pockets of gas are. Deviations in wavelength indicate motion, allowing astronomers to trace where the molecules drift within the stellar winds. It is the closest thing we have to watching chemistry happen in real time inside a star. Webb has revealed carbon chains that vibrate in ways that match laboratory models. It has identified dust precursors that glow just slightly off from expected wavelengths, hinting at unusual temperatures or unexpected formations. Some molecules appear warped by collisions, others appear pristine. Each one is a clue in a puzzle that spans physics, chemistry, and stellar evolution. And the most astonishing part is this. Many of these signatures were invisible to previous telescopes. The Hubble Space Telescope, remarkable as it is, simply couldn't see this deep into the infrared. Ground-based telescopes were overwhelmed by atmospheric noise. For decades, these spectral fingerprints existed but lay hidden, like text written in ink too faint to read. Webb changed that. Its detectors cooled to a few degrees above absolute zero eliminate thermal noise. Its segmented mirror captures more light than any space telescope before it. Its position beyond Earth's warmth gives it a vantage point untouched by our atmosphere. It reads starlight the way a jeweler examines gems, turning them, splitting them. This precision opens the door to something profound. We can now test ideas that were once purely theoretical. How do molecules behave when trapped between shock waves? How fast do they form on dust grains? How quickly do they evaporate in rising plumes of heat? These are questions we could never ask before, because we had no data fine enough to answer them. Webb's spectrum is not just data. It is a translation key. It is the Rosetta Stone that reveals the impossible as real, the unthinkable as measurable, and the forbidden chemistry inside stars as a legible, decipherable story written in light. Under normal physics, stellar temperatures should destroy complex structures instantly. For decades, astronomers have treated the atmospheres of stars as chemical deserts, places where atoms exist mostly as stripped nuclei and free electrons, with little hope of forming anything more elaborate. The idea that complex molecules could endure here, even for a moment, contradicts everything we understand about thermodynamics, radiation, and atomic behavior in extreme environments. To appreciate how impossible this is, consider the physics at play. In many stellar atmospheres, temperatures range from 3,000 to 30,000 degrees Celsius, hot enough to unbind molecules in trillionths of a second. Even the strongest chemical bonds, like the carbon-carbon double bonds found in organic molecules, snap instantly at these energies. Ultraviolet radiation tears electrons from atoms. Collisions happen at velocities that mimic microscopic explosions. Nothing delicate should survive this bombardment. And yet, Webb's spectra show clear evidence that they do. Carbon chains, long, fragile sequences of atoms, appear to persist long enough for Webb to detect the unique vibrational signatures they imprint on starlight. This means molecules are not merely flickering into existence for an instant and vanishing. They are surviving for measurable periods of time. Not long on human scales, of course, but long enough to be seen across hundreds of light years, long enough to challenge our models. The simplest explanation is that our picture of stellar atmospheres is incomplete. Traditional models treat these layers as smooth gradients of temperature and density, predictable and uniform. But increasingly, Webb's data paints them as chaotic mosaics, pockets of cool gas embedded in hot plasma, turbulent eddies separated by thin boundaries where temperatures plummet unexpectedly. In those boundaries, the rules shift just enough for molecules to form and, more importantly, to survive. Another key factor may be shielding. Dust grains or clusters of ions could protect molecules from direct radiation, acting as tiny parasols in an otherwise merciless storm. Even a thin shield can reduce the destructive impact of high-energy photons long enough for chemical interactions to take place. If molecules cling to the surfaces of dust particles, they may occupy microzones where temperatures briefly drop into the survivable range. But even these explanations feel insufficient. They account for formation, but not endurance. They explain the spark, but not the flame. More exotic ideas propose that magnetically confined regions could create both physical and thermal barriers within the atmosphere, tiny cavities where plasma density drops and heat dissipates. In these cavities, molecules might last longer than expected, trapped behind magnetic curtains that filter out the worst of the star's radiation. Some scientists even speculate that certain molecules might self-stabilize under intense stellar conditions. In rare circumstances, energy absorbed from the environment might be redistributed across the molecule in ways that prevent immediate destruction, a kind of molecular shock absorber that temporarily dampens the violence around it. Whatever the mechanism, the implications are profound. If molecules can survive where they should not, then the islands of stability inside stars may be more numerous, more durable, and more chemically active than we ever imagined. The birthplace of molecules might not be limited to cold interstellar clouds, but could begin in the incandescent breaths of stars themselves. And every time Webb catches another forbidden molecule shimmering inside a stellar atmosphere, it sends a clear message. Something fundamental is missing from our understanding of stars. A new chapter of stellar physics is waiting to be written, one that embraces complexity in places we once assumed only chaos could rule. Astronomers now suspect there are microregions where temperatures plunge by thousands of degrees, brief windows where chemistry awakens. These are not stable environments or long-lived oases of calm. They are momentary collapses in temperature, like the quick breath of cool air that follows the crack of a lightning bolt. In the vast, violent atmosphere of a star, these microregions act as fleeting sanctuaries where atoms can meet, bond, and form structures that should never exist in such hostile conditions. This phenomenon, nicknamed the cosmic refrigeration effect, is one of the most surprising implications of Webb's findings. It suggests that the outer layers of certain stars are far more thermally complex than previously thought. Instead of a smooth gradient from scorching interior to cooler exterior, the stellar atmosphere may resemble a boiling cauldron where pockets of gas expand suddenly, causing rapid and dramatic drops in temperature. To understand how this works, picture a mass of superheated gas rising from deep within the star. As it ascends, pressure decreases sharply. When gas decompresses quickly enough, it cools, sometimes dramatically. In the atmosphere of a star, this cooling can happen in milliseconds, creating temperature drops of thousands of degrees. The gas is still hot by earthly standards, but compared to its surroundings, it becomes a cold spot, a temporary pocket of hospitable conditions for molecular formation. This cooling is enhanced by shock waves. When two turbulent flows collide, or when rising plumes smack into falling ones, the sudden shift in pressure can trigger a rapid expansion of gas on one side of the interaction. That expansion acts like the release of a compressed spring, energy spreads out, and temperature falls. For a moment, the furious heat of the star gives way to a tiny envelope of relative calm. Inside these microregions, chemistry seizes its chance. Atoms that normally ricochet off one another with the force of microscopic explosions suddenly slow down just enough for bonds to form. Carbon chains link together. Dust seeds crystallize. Molecular clusters emerge. None of it lasts long, but it does not have to. Webb's instruments reveal these fleeting chemical signatures because the molecules imprint themselves on starlight almost instantly. Some astronomers propose that radiative cooling amplifies the effect. Certain molecules, especially carbon-based ones, radiate away heat extremely efficiently. As soon as they form, they can help cool their own surroundings even further, creating a feedback loop that grants them just a little more time before the next wave of heat washes over them. In this sense, the molecules become both products and participants in the refrigeration process. Magnetic activity may also play a role. Stars with strong magnetic fields can create funnels or arches where plasma becomes trapped and insulated from hotter layers. Within these magnetic corridors, expansion-driven cooling may be intensified, stretching the lifespan of the microregions long enough for more complex chemistry to take place. What makes the cosmic refrigeration effect so paradigm-shifting is its scale. These microregions are tiny compared to the star, and they live for milliseconds. Yet the molecules formed within them influence stellar winds, dust production, cooling rates, and the eventual dispersal of chemically rich material into interstellar space. In other words, brief molecular flashes inside stars may have consequences that ripple across the galaxy for billions of years. The cosmic refrigeration effect reveals a startling truth. Stars are not uniform furnaces. They are turbulent ecosystems filled with hidden, transient microclimates, tiny windows where physics bends just enough for chemistry to bloom. Inside stars, turbulence might create swirling pockets, where gas becomes temporarily shielded from the star's fury. These pockets, eddies born from chaotic flows, twist and fold through the stellar atmosphere like whirlpools in a cosmic ocean. They are small, transient, and invisible to the eye, yet they may be among the most important environments for chemical complexity anywhere in a star. Turbulence inside a star isn't gentle. It is violent, driven by convection currents rising from deep below the surface. Hot plasma surges upward, cools, and sinks back down, creating massive circular motions. When these flows collide or shear past each other, they generate eddies, swirling vortices of gas that carve out tiny microenvironments with very different conditions from the surrounding plasma. In these eddies, gas can become trapped long enough to escape the full brunt of the star's heat. Temperatures may drop by thousands of degrees compared to the surrounding environment. Pressure may stabilize, collisions may slow, and even though this respite is short-lived, lasting milliseconds or seconds at most, it is enough for molecules to form, survive, and imprint their spectral signatures on the starlight streaming outward. Imagine a leaf caught in a whirlpool in a raging river. The water around it is fast, chaotic, destructive, but inside the vortex, the leaf is sheltered, circling calmly, protected from the worst of the current. Inside these stellar eddies, atoms and molecules experience a similar momentary sanctuary. They swirl in gentle arcs, even as the outer atmosphere roars around them. Scientists have long known that turbulence plays an important role in the movement of gases inside stars, but Webb's discoveries suggest it also plays a role in chemistry. The swirling motions can isolate gas from incoming heat. They can reduce interactions with ionizing radiation. They can shield newly formed molecules from collisions energetic enough to rip them apart. In effect, eddies inside stars may act as micro-laboratories, places where chemistry can proceed more calmly than anywhere else in the stellar environment. Some models suggest that these eddies can even sort material by density. Heavier particles, like dust grains, drift toward the center of the vortex, where they remain cooler and more protected. Lighter gas circulates around the edges. This separation may allow dust grains to accumulate and act as nucleation sites for molecular formation, supporting the idea that dust and turbulence work hand in hand to build complex structures. The presence of turbulent chemical havens also helps explain why molecules appear in clusters rather than evenly distributed across the star's atmosphere. Webb sees patches, localized regions where molecules thrive. These patches may be the surface expressions of deeper vortices, bubbles of sheltered gas rising toward the surface and carrying their fragile chemistry with them. And the implications stretch far beyond one star or one discovery. If turbulent eddies are common, then molecular formation inside stars may be widespread across the galaxy. Every giant star, every aging red supergiant, every pulsating variable may host these swirling pockets of chemical activity. Over millions of years, these stars could release vast amounts of dust and molecules into the interstellar medium, enriching the galaxy with ingredients for planets and life. In the end, turbulent eddies reveal something profound. Even inside the most extreme environments in the universe, complexity can find a way. Hidden inside swirling currents of plasma, protected by the physics of motion itself, chemistry unfolds quietly in the very places we once thought were barren. These unexpected molecules might be the missing link in understanding how stars shed their outer layers into space. For decades, astronomers have struggled to explain why some stars lose mass far more rapidly than theoretical models predict. Mass loss isn't just a detail. It shapes how stars evolve, how they die, and what kind of remnants they leave behind. Now, with Webb's discovery of forbidden molecules, a new idea is emerging. Perhaps molecules themselves are helping stars peel away their outer layers. Mass loss begins at the surface, where rising plumes of gas push outward against gravity. In standard stellar models, this process is driven largely by radiation pressure, light pushing against atoms and dust. But radiation alone cannot account for the enormous mass lost by some red giants and supergiants. Something else must be at work, providing that extra push. And this is where molecules enter the story. Certain molecules, especially carbon-rich chains and dust precursors, are incredibly efficient at absorbing and re-radiating stellar light in the infrared. When they form in the atmosphere, they act like tiny sails catching the star's radiation. This creates an outward force, not enormous, but significant, helping lift gas away from the stellar surface. Over millions of years, the cumulative effect of countless molecules may accelerate mass loss dramatically. The pattern Webb revealed, molecules clustering in specific layers, matches perfectly with regions where mass loss is known to be strongest. These molecular zones form just above the convective plumes that push material outward. As molecules attach to dust grains, they increase the grain's ability to capture light. The grains then drift outward more quickly, dragging gas along with them. It becomes a subtle but powerful chain reaction. Chemistry aiding motion, motion aiding more chemistry. Shockwaves, turbulence, and pockets of cooling gas, phenomena discussed in earlier segments, become even more important in this context. Each one contributes to molecule formation, and each new molecule strengthens the star's ability to lose mass. The very processes that enable forbidden chemistry may also be the engines driving a star's slow unraveling. This explains why stars nearing the end of their lives lose mass at such astonishing rates. As they expand and cool, molecular formation becomes easier. Shock waves grow stronger. Dust forms more readily. The atmosphere becomes a rich environment for chemistry, which in turn fuels even more mass loss. A runaway feedback loop begins. More molecules lead to more wind. More wind exposes deeper layers. Deeper layers produce even more molecules. Understanding this cycle also helps unravel mysteries about the shapes of planetary nebulae, the glowing shells of gas shed by dying stars. Webb's detection of molecular clusters may explain why these nebulae often display intricate patterns, rings, and arcs. If molecules form unevenly in the atmosphere, then the mass loss will be uneven too, imprinting chemical textures on the gas as it escapes. Even supernovae, the dramatic deaths of massive stars, are influenced by mass loss. The density of the outflowing material affects how the shockwave travels, how the star explodes, and which elements escape into space. Molecules may determine whether a star ends as a bright supernova, a dim one, or something stranger. The implications ripple outward: the dust that becomes planets, the carbon that becomes life, the heavy elements scattered across galaxies, all may owe their existence, in part, to molecules forming inside stars long before those stars die. Forbidden molecules are not just chemical curiosities. They are clues, delicate, glowing fingerprints that reveal how stars shed their skins and return their material to the cosmos. Molecules could be the earliest building blocks of cosmic dust, the material that seeds planets, moons, and even life. Dust may seem trivial, like the cosmic equivalent of soot, but in reality, it is the scaffolding upon which worlds are built. Every rocky planet, every asteroid, every icy moon began as dust grains drifting between the stars. And now, thanks to Webb's unprecedented sensitivity, we're learning that the story of dust begins much earlier and in far stranger places than we ever imagined. The traditional picture places dust formation in the cool, extended atmospheres of dying stars, giants that have swollen and cooled enough for atoms to condense into solids. But Webb has shattered that old view by finding molecular precursors much deeper in the stellar envelope, far closer to the scorching surface where dust should be impossible. These molecules are the first steps towards solid grains, carbon chains, silicon clusters, metal oxides, tiny structures that gather, link, and crystallize into dust. The presence of such molecules means dust may begin forming in the very regions where stars are still roaring with heat. It's as if bricks are being assembled in the furnace rather than waiting for the kiln to cool. This early formation dramatically alters our understanding of how stars enrich the galaxy with solid material. Inside these stellar envelopes, chemistry unfolds like a carefully orchestrated sequence. First come simple molecules, carbon dimers, silicon monoxide, metal hydrides. Then, as the gas cools in turbulent pockets or shock-cooled zones, these molecules chain together. Carbon atoms form long, flexible skeletons. Silicon and oxygen combine into rigid clusters. Metals fuse into crystalline seeds. Each tiny structure acts as the nucleus of a future dust grain. But the process doesn't stop there. Once these molecular seeds exist, they grow rapidly. Gas atoms stick to them like frost on a window pane, adding layer after layer. Turbulence mixes the surrounding gas, feeding new material to the growing grains. Stellar winds lift them outward, where temperatures continue to drop. By the time they leave the star's immediate environment, they are solid particles, microscopic worlds in their own right. These grains don't simply float away and vanish. They play a pivotal role in shaping the interstellar medium. Dust helps cool gas clouds, enabling gravity to collapse them into new stars. Dust shields fragile molecules from radiation, allowing complex chemistry to flourish. Dust provides the raw material for planet formation, clumping into pebbles, rocks, and eventually entire worlds. If dust formation starts earlier than we thought, then the universe may have become fertile with planet-forming material sooner than models suggest. Even the first generations of stars, ancient giants that died long before the sun was born, may have produced more dust than expected, enriching the young universe with the ingredients for planetary systems. Webb's discovery also hints that stars may differ widely in their dust-making abilities. Some may be prolific dust factories, generating enormous quantities of grains that feed nearby nebulae. Others may produce only thin traces. Understanding which stars contribute most to cosmic dust budgets may reshape how we understand galaxy evolution as a whole. And then there is the connection to life. Many of the organic molecules essential for biology, carbon rings, hydrocarbons, amino acid precursors, form on the surfaces of dust grains. If dust begins forming inside stars, then the earliest sparks of biochemistry may originate not in cold molecular clouds, but in the glowing envelopes of dying suns. The birth of dust is more than a physical process. It is the universe's way of gathering ingredients, preparing them, and sending them outward to become planets, oceans, atmospheres, and eventually, living things asking how it all began. Magnetic arches rising through the star may trap cooler material, forming channels where molecules persist. These arches, vast loops of magnetized plasma, tower above the stellar surface like cosmic suspension bridges, guiding charged particles along invisible rails. To the naked eye, they are nothing but light, but in reality they form structured corridors where the chaotic violence of the star softens just enough for fragile chemistry to take root. Inside most stars, magnetic fields twist and coil as they rise, erupting through the surface in arcs that can span hundreds of thousands of kilometers. On our own sun, these loops help shape coronal mass ejections and solar flares. But on larger, more turbulent stars, their influence may stretch much deeper into the atmosphere, and it's here that Webb's findings become extraordinary. For years, astronomers suspected that magnetic fields could generate sheltered pockets in stellar atmospheres, but no telescope had the resolution or sensitivity to detect what might be happening inside them. Webb changed that. Its infrared vision has revealed spectral hints that molecules cluster not randomly, but along narrow regions that align suspiciously well with where magnetic channels are expected to form. These magnetic corridors act as stabilizing structures in an otherwise unstable environment. Hot plasma is funneled upward along the field lines, but cools as it rises, unable to freely mix with the hotter surroundings due to magnetic confinement. The result? Thin, elongated zones where temperatures drop by thousands of degrees, protected from the crushing turbulence and radiation outside. Inside these zones, atoms slow down. Collisions become less violent. Chemical bonds, normally shattered instantly in the open atmosphere, linger long enough for molecules to form. Some may cling to dust grains. Others may float freely, drifting upward in the slow, magnetically guided flow. The magnetic shielding doesn't just reduce temperature, it also creates a physical barrier. Plasma outside the loop cannot easily cross the field lines, meaning the molecules inside are partially insulated from disruptive collisions. This gives them time, brief by human standards, but ample in the world of quantum chemistry, to produce the vibrational signatures Webb detected. Magnetic loops may also act as conveyor belts. As molecules form in the cooler lower sections, they are lifted upward along the loop, carried into even cooler regions where their survival is extended. It's a delicate balance: rise too quickly, and they are exposed to radiation, linger too long in a hot region, and they evaporate. But the geometry of the magnetic arches provides just the right combination of shielding and transport for these fragile structures to leave their mark on the star's escaping light. This process could be widespread. Many evolved stars, especially red giants and asymptotic giant branch stars, display strong magnetic behavior. Some exhibit gigantic arcs that dwarf the loops on our sun. If magnetically sheltered zones are common, then molecular survival could be far more frequent than we ever realized. And the implications go beyond chemistry. Magnetic field-driven mass transport affects stellar winds, dust formation, pulsation cycles, and even the ultimate fate of the star. Molecules forming within magnetic channels may be the seeds that eventually become dust grains. Those dust grains may help drive mass loss. That mass loss shapes the star's evolution and determines what elements it contributes to the galaxy. In this way, magnetic fields may be the silent architects behind the forbidden chemistry we now observe. By sculpting hidden corridors of stability inside a furnace of plasma, they enable molecules to persist where nature seems to forbid them. Inside those glowing arches, stars reveal that even in their most chaotic moments, they possess the structure and the subtlety to shelter the beginnings of complexity. The survival of these structures forces scientists to reconsider where thermodynamic limits lie inside stars. For more than a century, stellar physics has relied on a set of assumptions that seemed unbreakable. Extreme heat destroys complexity, molecular bonds cannot survive beyond a certain threshold, and chemical reactions in stars are simple, fast, and brutally efficient at tearing matter apart. But Webb's discoveries are painting a different picture, one where the traditional boundaries of thermodynamics blur under the weight of chaotic, real-world conditions. In theory, the temperatures in stellar atmospheres should be overwhelmingly hostile to molecular structure. Chemical bonds require stability. They depend on balance, energies that are low enough to allow atoms to join but high enough to avoid freezing into rigid forms. Inside a star, that balance should be impossible. Thermal motion is so intense that even a single collision can inject enough energy to obliterate a molecule. The kinetic energy of gas particles overwhelms bond strengths by orders of magnitude. And yet, against all expectations, molecules endure. This defiance hints that the thermodynamic picture we've constructed may be too simplistic. Thermodynamics excels at describing average conditions, bulk properties over time. But inside stars, nothing is average. Instead, conditions fluctuate wildly from one microscopic region to the next. Temperatures spike and plummet, densities surge and collapse. Gas expands violently in one layer and compresses in another. Magnetic fields twist and contain plasma. Shock waves sweep through, momentarily altering local environments. In such a chaotic system, classical thermodynamic averages may conceal the extreme variability that actually governs molecular survival. If temperature in a small pocket drops by thousands of degrees for even a millisecond, chemistry can ignite before the larger environment reasserts control. These pockets may be statistically rare, but their effects accumulate across billions of atoms and millions of years. Another complication comes from radiation. In stellar atmospheres, radiative transfer is far from uniform. Certain molecules absorb very specific wavelengths of light, wavelengths that transport heat out of the gas more efficiently than surrounding processes. When such a molecule forms, it can act as a tiny cooling agent, radiating heat away and lowering the temperature of its immediate environment. This can temporarily shift local thermodynamic conditions away from the global average, making bond formation more favorable. In a sense, the molecules help create the conditions that allow more molecules to form. Dust grains add another layer to the puzzle. Their surfaces can act as energy sinks, absorbing excess heat and stabilizing chemical bonds. Reactions that would be impossible in the open plasma might succeed on the surface of a grain before being swept to safety by stellar winds. Classical thermodynamics assumes a uniform medium, but dust grains break that uniformity, providing countless tiny islands where normal rules soften. And then there's turbulence. Real stellar atmospheres are not stratified, static layers. They are violent flows. Turbulence creates shear zones, vortices, and eddies where temperature gradients flip rapidly. In these zones, the gas may not reach thermodynamic equilibrium at all. If equilibrium never exists locally, then the thermodynamic rules governing equilibrium cannot fully predict the behavior of that region. This realization is profound. Molecules inside stars are not defying physics. They are revealing a more intricate version of it. a version where microenvironments matter just as much as large-scale averages, where transient conditions shape long-term outcomes, and where chemistry thrives not by resisting thermodynamics but by exploiting its overlooked subtleties. In short, molecules inside stars rewrite our understanding of what thermodynamic limits truly mean. They remind us that even inside a furnace, the universe finds pockets of possibility. Different stars show different molecular fingerprints, suggesting the phenomenon isn't isolated to one type of stellar furnace. At first, astronomers believed these forbidden molecules might only appear in the swollen atmospheres of cool red giants, where temperatures are comparatively mild. But Webb's observations have revealed something far more intriguing. Molecular signatures also appear, faintly but unmistakably, around stars that should be far too hot to permit such complexity. The implication is staggering. This is not a quirk of a single stellar species. It may be a universal feature of stellar evolution. Red giants and blue giants could not be more different. Red giants are bloated, cool, slow-burning stars in their twilight years. Their atmospheres are extended and loosely bound, with temperatures low enough to allow molecules, water vapor, carbon chains, metal oxides to form naturally in their outer layers. Blue giants, on the other hand, are blazing titans. They burn hot, bright, and fast. Their surfaces can exceed 30,000 degrees Celsius, radiating ultraviolet light so intense it can ionize atoms in an instant. By all accounts, they should be molecular deserts. And yet, Webb detects faint traces of molecules near both. In red giants, the process is somewhat expected, but even here, the molecule types challenge assumptions. Webb finds long carbon chains and unusual dust precursors deeper in the atmosphere than previously thought, in regions where temperatures are still hostile. This hints at complex interactions between convection, shock waves, and cooling pockets that allow chemistry to flourish far below the traditional molecular zone. But the blue giants are where the real mystery lies. Blue giants are extreme in every sense. Their atmospheres are compact and fiercely hot. Their radiation fields are intense enough to strip electrons from atoms hundreds of kilometers away. Yet Webb detects tiny molecular imprints, thin, whisper-like absorption lines, suggesting that small pockets of cooler gas might hide within the chaos. These may be the same shock-cooled zones, magnetic funnels, and turbulent eddies found in red giants, but on a more compressed and violent scale. The fact that molecules appear in both types of stars suggests the underlying mechanism doesn't depend on temperature alone. Instead, it depends on structure, how gas moves, how magnetic fields twist, how shock waves propagate, how dust forms and survives. It suggests that even the hottest stars host microenvironments where chemistry flickers briefly into existence. This universality forces scientists to rethink stellar classification, not just in terms of color and temperature, but in terms of chemical potential. A star once considered too hostile for molecular survival may, in fact, produce entirely different classes of molecules, ones uniquely adapted to extreme conditions. Future Webb spectra may reveal distinct chemical fingerprints for each stellar type, forming a kind of molecular taxonomy of the cosmos. It also raises questions about the role these molecules play. In red giants, they may seed dust that eventually enriches galaxies. In blue giants, they may influence stellar winds, shaping how these massive stars lose mass before exploding as supernovae. Blue giants are responsible for creating many of the universe's heaviest elements. Iron, gold, uranium. If molecules play any role in how these stars evolve or shed their mass, then they indirectly shape the chemical makeup of the universe itself. In the end, Webb shows us that stars are not defined solely by size or temperature. They are complex ecosystems with hidden layers of chemistry. And whether a star glows cool red or blistering blue, the same surprising truth emerges. Where there is turbulence, motion, and just a hint of shelter, molecules will find a way to live, even inside a furnace. Near the final breaths of certain stars, molecular complexity grows instead of shrinking, a cosmic paradox. As these massive suns swell, dim, and prepare for their final transformations, one would expect their atmospheres to become increasingly chaotic and inhospitable. Shockwaves intensify, temperatures fluctuate wildly, layers of plasma peel away. Everything points toward destruction, an unraveling of structure as the star nears its end. And yet, Webb keeps revealing the opposite. The closer some stars get to death, the more chemically rich their atmospheres become. This phenomenon has puzzled astronomers for decades. Ground-based telescopes occasionally picked up faint hints of dust production around aging stars. Infrared satellites spotted flickering signs of simple molecules drifting through expanding stellar envelopes. But the data was always fragmentary, incomplete. Now, with Webb's unprecedented infrared resolution, the picture has sharpened. Dying stars glow with phantom molecules, fleeting structures that form on the edge of annihilation yet somehow thrive in the turmoil. These stars are not quiet giants slowly fading away. Many of them are variable stars, pulsating in rhythmic cycles that inflate and contract their atmospheres like living, breathing titans. Each pulsation sends shockwaves rippling outward, waves that compress gas, spark molecular formation, and then fling those molecules into cooler surrounding regions before they can be destroyed. It is as if the star coughs up pockets of complexity every time its outer layers quake. Even more astonishing is the diversity of molecules that appear during these final phases. Webb has detected carbon chains stretching far longer than previously thought possible. Silicon compounds, metal oxides, dust precursors forming deep inside stellar layers where theory insists they should instantly vaporize. It's a chemical crescendo, an unexpected blossoming of structure in the last chaotic chapters of a star's life. Why does complexity rise as death approaches? The answer lies in the interplay between cooling, expansion, and chemistry. As stars near the end of their lives, they often expand dramatically, causing their outer layers to cool. Even a modest drop in temperature can open doors for chemistry. Molecules that couldn't exist at 3,000 degrees might survive at 2,500. Add turbulence, shockwave compression, dust grain shielding, and magnetic confinement, and suddenly the atmosphere becomes a patchy tapestry of microenvironments. Some hot, some cool, some protected enough for molecular assembly. Meanwhile, the star's mass loss rate skyrockets. Outward flowing winds strip the atmosphere layer by layer, carrying molecules away before they can be destroyed. In a way, the dying star becomes a molecular fountain, expelling its chemistry into space, where it cools further and condenses into dust. This dust eventually drifts into interstellar clouds, seeding the ingredients for new stars and new planets. Some of the most chemically rich zones appear in asymptotic giant branch AGB stars. Elder suns swollen to massive, luminous shells. Webb has shown their atmospheres to be unexpectedly structured, with rings, arcs, and spirals shaped by pulsations and, in some cases, unseen companion stars. These features help concentrate molecules into dense clumps, enhancing formation and shielding them from destruction. The final paradox emerges in the star's transformation itself. As its core contracts and its envelope expands, the star enters a brief phase where its winds, cooling layers, and pulsations align perfectly to enable chemistry, just before the star sheds its atmosphere entirely and exposes the blazing core beneath. The molecules appear like ghosts, brilliant, short-lived, fading as the star sloughs off its last layers. Yet their legacy endures. Those phantom molecules become dust. That dust becomes raw material, and the star's final act becomes the first chapter in the story of new worlds. By tracking molecular signatures over time, astronomers can follow a star's life like rings in a tree stump. Each molecule, each spectral line, each faint indentation on a Webb infrared graph becomes a timestamp, a chemical echo of a specific moment in a star's evolution. For the first time in history, scientists are beginning to read these molecular imprints not as isolated curiosities, but as a chronological record of stellar change. The idea is simple but profound. As a star ages, the chemistry of its atmosphere transforms. Heat rises and falls. Winds strengthen and weaken. Dust begins to form. Shock waves ripple outward in predictable cycles. And through all these changes, molecules serve as markers, tiny chemical witnesses that reveal what the star is doing at any given stage. Early in a star's life, molecular signatures tend to be sparse or non-existent. Young stars burn too hot, too violently. Their atmospheres are compact and dominated by ultraviolet radiation that strips electrons and pulverizes bonds. But even in these early stages, Webb has identified the faintest hints of simple molecules forming in sheltered magnetic pockets, or shock-cooled layers. These early molecules hint at the beginnings of a more complex future. As stars grow older and expand into giants, their atmospheres cool and stretch outward. This is when molecular chemistry truly ignites. Different molecules form at different temperatures, in different layers, and under different dynamic conditions. The presence of carbon dimers may indicate early cooling. The appearance of carbon chains might signal stronger convection currents. Silicon monoxide clusters often precede dust formation. Metal oxides may flag changes in pulsation cycles. Each molecule tells a story. Carbon chains, for example, appear in mid-stage giants as they begin shedding mass. Dust precursors show up slightly later, marking the star's transition into the intense mass loss phase. Certain metal-bearing molecules emerge only during the chaotic pulsations near the end of the star's life, when shock waves become powerful enough to rearrange its atmospheric structure. Webb's sensitivity makes it possible to watch these changes unfold over surprisingly short timescales. Some stars pulsate on cycles of months or even weeks. During each cycle, molecular signatures fade, strengthen, or shift, providing astronomers with a chemical heartbeat, a rhythmic pulse that reveals how the star breathes. As the star expands, molecules form. As it contracts, some are destroyed. This molecular ebb and flow becomes a direct measurement of the star's internal dynamics. Over years and decades, these records add up. This molecular chronology also helps astronomers understand stellar populations across the galaxy. Two stars of similar mass might evolve differently if their molecular signatures diverge, suggesting differences in internal mixing, magnetic activity, or mass loss efficiency. Large surveys with Webb can compare thousands of stars, mapping molecular patterns onto evolutionary models and refining our understanding of how stars grow old. And the implications ripple outward. Because the molecules inside stars directly influence dust formation and mass loss, the chemical timeline of a star also becomes a predictor of its future. The molecules present today hint at whether the star will shed material gently or violently, whether it will form a planetary nebula or collapse into a dense remnant, and how much material it will contribute to future generations of planets and stars. In essence, molecules are not just passengers in a star's evolution. They are signposts. They trace the star's past, illuminate its present, and even hint at its destiny. By reading these chemical rings, astronomers are learning to understand stars not as static points of light, but as dynamic, evolving worlds, each one carrying its own molecular story written in starlight. These stellar molecules may be directly linked to the compounds found in young planetary systems. For years, astronomers assumed that the chemistry of planets began far from their parent stars, inside cold molecular clouds where dust clumped and cooled. But Webb's revelations paint a very different picture, one in which the earliest building blocks of planets trace their origins not to distant nebulae, but to the very atmospheres of the stars that birthed them. If this is true, then planet formation begins not in calm darkness, but in blazing starlight. The molecules Webb has uncovered, carbon chains, silicon clusters, metal-bearing compounds, dust precursors, are exactly the types of structures found in protoplanetary disks around young stars. These disks, swirling rings of dust and gas, eventually collapse into planets, moons, comets, and asteroids. The chemistry needed for their creation has always been present in these disks, but the origin of that chemistry was unclear. Did it come from earlier generations of stars? from interstellar clouds, or from the disks themselves? Webb's findings suggest a surprising answer. Much of it may come directly from the dying breaths of older stars. When a star nears the end of its life, its atmosphere becomes a rich chemical stew. Molecular structures flourish. Dust grains form by the trillions. Stellar winds accelerate, carrying this chemically enriched material into interstellar space. Over time, the winds from countless stars mingle, seeding the galaxy with the raw ingredients for new worlds. But the new twist is that this chemical enrichment may begin far earlier and far deeper than astronomers ever suspected. Instead of forming only in the cool outskirts of aging stars, molecules may begin assembling close to the stellar surface, even in stars that are still far from death. These molecules, mixed with dust, are then lifted outward by radiation pressure and stellar winds, joining the interstellar medium long before the star's final collapse. This means the material that eventually forms planets does not originate from cold space alone. Much of it forms while still immersed in the fires of stellar atmospheres. The implications ripple across cosmic history. If chemical complexity begins inside stars, then the timeline for planet formation shifts dramatically. The galaxy becomes chemically fertile much earlier. The first generation of planets may have emerged sooner, and the diversity of exoplanetary systems, rocky planets, gas giants, water worlds, carbon-rich worlds, may reflect the diversity of molecules forged inside their parent stars. It also explains a long-standing puzzle: why so many protoplanetary disks contain complex organics, polycyclic aromatic hydrocarbons, metal oxides, and crystalline silicates. These materials shouldn't form easily in cold disks, but they do form easily inside turbulent stellar atmospheres, where temperatures and pressures swing wildly enough to spark chemistry that cold environments simply cannot achieve. Webb's discovery suggests that the line between stellar chemistry and planetary chemistry is far thinner and far more connected than anyone realized. A molecule that forms in the sheltered eddy of a red giant's atmosphere may one day become part of a dust grain drifting into a young star's disk. That dust grain may clump with others, forming rocks, then planetesimals, then full-grown planets. Those planets may evolve atmospheres, oceans, magnetic fields, and in rare cases, life. In this way, the molecules Webb detects inside stars are more than anomalies. They are chemical bridges, threads connecting the lives of stars to the origins of planets, and the origins of planets to the possibility of life. The story of a world does not begin in the calm of a nebula. It begins inside stars. Webb's deep field surveys suggest early stars might have harbored similar chemical havens in their atmospheres. This discovery stretches the implications of forbidden chemistry across not just space, but time itself. If ancient stars, born when the universe was barely a few 100 million years old, hosted these fragile molecular structures, then chemical complexity began far earlier than anyone had dared to imagine. The early universe was once thought to be simple. After the Big Bang, the cosmos cooled into a sea of hydrogen and helium. Heavier elements, carbon, silicon, oxygen, didn't exist until the first massive stars forged them through nuclear fusion and scattered them in titanic supernova explosions. For decades, the consensus was clear. The early universe was too young, too hot, and too element-poor for molecules of any complexity to exist. But Webb is challenging that narrative. In its deep field observations, those haunting images that peer across billions of light years, Webb has revealed faint molecular signatures in the spectra of ancient galaxies. These galaxies are home to stars that formed when the universe was still in its infancy, stars whose light began its journey long before Earth existed. And yet embedded within that ancient starlight is something extraordinary: the fingerprints of molecules. These molecules appear in the atmospheres of early stars not as rare accidents, but as recurring patterns. The same carbon chains detected in modern stellar envelopes. The same dust precursors seen in aging giants. The same shock-cooled signatures, all echoed faintly in galaxies so distant their light is stretched into the infrared by the expansion of the universe. Webb's unparalleled sensitivity allows astronomers to pick out these faint traces, revealing that the turbulent, chaotic atmospheres of early stars may have formed the same kinds of chemical microclimates we see today. How could this be? The answer lies in the universality of physics. Even the earliest stars experienced turbulence. They pulsed, they convected, they generated magnetic fields, they produced shock waves. As soon as stars existed, the same chaotic ingredients that fostered dark chemistry in modern giants were present. And once the first supernovae seeded the cosmos with carbon and other elements, even in tiny amounts, there was enough raw material for molecular chemistry to ignite inside stellar atmospheres. What's more, early stars were often larger and more massive than stars today. This may have produced even stronger cooling pockets, shock-driven turbulence, and dust formation pathways. In other words, the early universe may have been richer in forbidden chemistry than the modern one. This realization reshapes our understanding of cosmic evolution. It means the first dust grains may have formed earlier than we believed. This dust played a vital role in cooling early gas clouds, allowing the first galaxies to grow. Planet formation could have begun sooner. If dust and molecular precursors existed early on, the timeline for building rocky worlds shifts dramatically. The chemical foundations of life may be older than Earth itself. Complex organic molecules often form on dust grains. If such grains existed near the universe's dawn, the seeds of biochemistry may stretch back nearly 13 billion years. And perhaps most astonishing, the universe was never chemically simple. Even in its first billion years, it may have been running a quiet, hidden chemistry lab inside its earliest stars, a place where atoms linked together in fleeting microclimates, writing the first chemical chapters long before galaxies matured. Webb is revealing that the cosmos became complex not late, but early, not slowly, but explosively, and the forbidden molecules glowing inside ancient stars are the whispers of that primordial creativity. If stars can produce complex molecules, the raw ingredients for biology could be far more widespread than we thought. For decades, the search for life's origins has focused on cold, dark places, molecular clouds, icy comets, primordial oceans. These environments seem gentle enough for fragile chemistry to flourish. But Webb's discovery of molecules forming inside the fiery atmospheres of stars changes that equation profoundly. It suggests that biology's essential ingredients may be forged not only in the quiet corners of the cosmos, but in the blazing hearts of stellar giants. Life as we know it relies on a toolkit of key molecular structures: carbon chains, aromatic rings, metal-organic complexes, water-bearing compounds. Many of these begin as dust grains coated with simple molecules, which then evolve through more complex chemistry in interstellar space. Until now, astronomers believed this early chemistry occurred exclusively in cold environments, where molecules could survive long enough to grow. But Webb has shown that the birthplace of these molecules may be far more diverse and far more violent than previously imagined. If stars can produce molecular seeds, then they become far more than forges of elements. They become forges of precursors to life. Inside turbulent stellar atmospheres, carbon atoms link together in fleeting oases, created by shock waves, magnetic confinement, and sudden temperature drops. These chains may only live for seconds, but that's long enough for stellar winds to sweep them outward, carrying them to cooler regions where they stabilize, grow, and eventually become dust grains. At that point, the chemistry accelerates. These dust grains drift into interstellar clouds, where they serve as scaffolds for more complex organic molecules: methanol, formaldehyde, even amino acid precursors. Every step of this pathway, once thought to occur only in cold space, may now begin inside stars. And this matters because it widens the cosmic canvas on which life's ingredients can form. If only a small fraction of stars hosted molecular chemistry, life's chemical precursors might be relatively rare. But if nearly all stars, red giants, blue giants, pulsating variables, ancient suns, can produce molecular building blocks, then the galaxy becomes chemically rich on a scale we never appreciated. It also shortens the timeline for life's essential ingredients to appear. The earliest stars exploded rapidly, spreading their enriched guts across the young universe. If those stars already produced molecules before they died, then the very first dust grains, the very first carbon networks, the very first organic seeds may have emerged only a few 100 million years after the Big Bang. That is astonishingly early. It means the cosmos began assembling the raw materials for biology long before Earth or even the Milky Way existed. And then those materials drift, mix, and settle into new systems. Newly forming stars inherit them. Protoplanetary disks integrate them. Planets accrete them. And somewhere, on at least one world we know of, life emerges. In this cosmic chain, stars are not distant, indifferent furnaces. They are active participants in life's long prelude, scattering molecular gifts across the galaxy. Webb has shown us that the line between astrophysics and biology is much blurrier than we thought. The atoms in our bodies, the carbon in our cells, the dust that formed our planet, all may trace their lineage not merely to the nuclear cores of ancient stars, but to their chemistry as well. The universe, it seems, does not wait for perfect conditions to create the ingredients for life. It creates them wherever it can, even inside the fire. Scientists now propose an entirely new field, stellar molecular chemistry, to study reactions inside stellar environments. For decades, the very idea would have felt contradictory, almost humorous. Stars were supposed to be places of nuclear fire, not chemical subtlety. Their atmospheres were assumed too violent, too hot, too chaotic for molecules to exist, much less participate in meaningful reactions. Chemistry belonged to cold, dark nebulae. Stars, we believed, belonged solely to the realm of fusion. But Webb's discoveries have shattered that divide so thoroughly that researchers are now charting a new scientific frontier, one that blends astrophysics, quantum chemistry, thermodynamics, and plasma physics into a single breathtaking discipline. At the heart of this emerging field lies a profound shift in perspective. Stellar atmospheres are no longer seen as smooth gradients of heat and density, but as complex environments filled with microclimates and hidden structure. Shock waves carve cooling passages. Turbulence twists gas into sheltered vortices. Magnetic arches lift cooler plasma into protected channels. Dust grains crystallize in improbable regions. Within these small, fleeting pockets, molecules form, survive, and even influence the larger behavior of the star. Stellar molecular chemistry seeks to understand these processes. It asks how molecules behave when immersed in plasma, how sudden drops in temperature alter reaction pathways, how turbulence shapes survival times, and how magnetic fields can find cooler pockets long enough for chemistry to awaken. It examines how radiation pressure acting on tiny molecular structures helps push stellar winds outward, and how dust grains assembled in these hidden chambers begin growing into the building blocks of planets. It even raises the question of whether complex organic structures, ringed molecules, perhaps even basic prebiotic compounds, could begin forming inside stars themselves. To explore these ideas, scientists rely heavily on advanced computational models capable of simulating molecular behavior in extreme heat. These simulations track how molecules vibrate, rotate, stretch, and fragment when bombarded by ultraviolet light or trapped between shock waves. Each model is compared to Webb's exquisitely detailed infrared spectra, creating a feedback loop that continually refines our understanding of these exotic chemical pathways. What emerges is a picture of chemistry that is neither terrestrial nor interstellar, but something entirely new. A chemistry that thrives under extreme pressure, fluctuating temperature, and intense radiation. It is not governed solely by equilibrium, but by turbulence, magnetism, and rapid environmental shifts. Molecules appear and vanish in cycles, driven by the pulsing of the star itself. This fusion of disciplines reveals that stellar chemistry plays an enormous role in shaping the galaxy. Molecules formed inside stars help cool their atmospheres, alter their winds, and influence their evolutionary paths. When these molecules become dust, they drift into interstellar space, cooling gas clouds, shaping nebulae, and ultimately becoming the raw material for planets and life. Stellar molecular chemistry is not merely about understanding stars, it is about understanding the entire chain of cosmic creation. The field is young, its boundaries still fluid, its textbooks unwritten. But the discoveries unfolding now suggest that stars are not chemically barren at all. They are molecular laboratories woven from fire and turbulence, quietly shaping the ingredients of galaxies long before these ingredients drift into the dark. A new science is emerging. And with every spectrum Webb records, it grows stronger. Teams have already identified dozens of stars where Webb will hunt for matching chemical fingerprints. These aren't random choices but carefully curated targets. Stellar giants, variables, supergiants, and even a handful of young stars whose temperaments hint that they may host hidden pockets of impossible chemistry. Webb has only just begun its survey, yet the early results have electrified the scientific community. If one star can harbor forbidden molecules, it is remarkable. If dozens do, it becomes a pattern, a phenomenon, a new chapter in astrophysics waiting to be written. The next targets range across the entire Hertzsprung-Russell diagram. Some are immense red supergiants nearing the end of their lives, swelling outward in great pulsing breaths that shake their atmospheres like drums. Their turbulent surfaces are ideal testing grounds, rippling with shock waves, convection currents, and rising plumes that may host cool pockets where molecules form. Webb's instruments will dissect their starlight layer by layer, searching for the faint dips in the spectrum that betray carbon chains, dust precursors, or silicate clusters. Other targets are hotter and far more surprising. Teams have flagged several blue supergiants, their surfaces blistering with temperatures that should reduce molecules to ash long before they can assemble. Yet early hints, barely perceptible wobbles in archived infrared spectra, suggest that even these scorching giants may harbor microregions where temperatures plunge just long enough for chemistry to flicker to life. If Webb confirms molecules in these stars, it would overturn assumptions about the upper limits of molecular survival and expand the playground of chemistry into realms once thought completely barren. There are also pulsating stars, specifically mirror variables, whose rhythmic expansions and contractions generate powerful shockwaves in their atmospheres. These stars act like cosmic bellows, compressing and cooling gas in cycles that may foster molecular formation. Webb will follow these pulsations over months, capturing the rise and fall of molecular signatures as the atmosphere breathes. If patterns emerge, if molecules appear and vanish in sync with the pulsation, scientists will gain unprecedented insight into how chemistry evolves in real time inside a stellar envelope. Some of the most intriguing targets lie in binary systems. When two stars orbit close together, their winds collide in vast arcs that compress gas into dense, turbulent shells. Past telescopes have spotted dust forming in these interaction zones, glowing faintly with thermal radiation. Webb's mission is to probe deeper, searching for the molecular skeletons that precede dust. If it finds them, it will confirm a long-standing suspicion that the clash of stellar winds may be one of the most fertile environments for forbidden chemistry in the galaxy. And then there are the stars Webb has yet to study, ancient giants in distant galaxies, their light stretched into the infrared by billions of years of cosmic expansion. Webb's deep field campaigns will examine these stars with the same spectral precision it brings to nearby ones, looking for echoes of the same molecular patterns. If the same chemistry appears in galaxies separated by unimaginable distances, it would suggest that forbidden molecular formation is not just local or rare, it is cosmic, woven into the fabric of stellar evolution itself. This next phase of Webb's mission is more than a survey. It is a search for a unifying thread, a chemical signature that binds stars across ages and galaxies. Each new target offers a chance to confirm that the impossible is not the exception, but the rule. And with every star Webb observes, our picture of the universe grows more intricate, more dynamic, and far more alive than ever before. Some astronomers suspect the observed structures may be precursors to polycyclic aromatic hydrocarbons, complex rings central to organic chemistry. These molecules, often abbreviated as PAHs, are among the most important structures in the universe. They form the backbone of countless organic compounds, including some essential to prebiotic chemistry. Their appearance has always been associated with cooler regions, nebulae, molecular clouds, or the soot-filled aftermath of dying stars. To even consider that precursors to these intricate ringed molecules might form inside a living star is nothing short of astonishing. Yet Webb's data is pushing scientists in that very direction. The carbon chains detected in stellar atmospheres are longer and more stable than expected. Some show spectral signatures that resemble transitional states, structures that sit between simple linear chains and the first closed rings. These are delicate formations, unstable on Earth but surprisingly resilient in the sheltered microclimates of a star's atmosphere. They hint at chemistry unfolding step by improbable step, guided not by calm lab conditions but by turbulence, shock waves, and sudden bursts of cooling. The idea is bold. Inside a furnace where heat should erase all complexity, carbon atoms may be dancing toward the first stages of aromaticity. The process begins with simple chains, 2 carbons, then 3, then 5 or more. As they lengthen, their structures become flexible, folding and bending under thermal motion. In certain conditions, especially in pockets where temperatures plunge, they can curl into loops. These loops represent the earliest form of ring structures, and once a ring forms, even briefly, it becomes a stable platform for further chemistry. More carbon atoms can join, additional rings can fuse, complexity accelerates. This is exactly how PAHs are believed to form in cooler environments, but Webb is showing that similar conditions may exist, fleetingly, inside stars. And those fleeting moments may be enough. Some astronomers argue that if even a small fraction of these precursors survive long enough to be swept outward by stellar winds, they could stabilize further in cooler layers. Once beyond the furnace, the rings could grow, stacking or linking into the more complex structures that Webb and other telescopes routinely observe in interstellar space. If this is happening, the origin of PAHs and potentially many other organic molecules might be shifted deep into stellar atmospheres rather than the interstellar medium alone. This idea also solves a long-standing puzzle. The galaxy contains enormous amounts of PAHs, far more than traditional models of cold cloud formation can explain. If stars themselves contribute directly to this molecular reservoir, the numbers begin to make sense. Every dying star could be a chemical factory, releasing aromatic seeds that drift into space, ready to play their role in the chemistry of future planets. The implications reach into astrobiology. Aromatic hydrocarbons are not life, but they are essential ingredients in the chemistry that leads to it. They absorb ultraviolet light in ways that stabilize more fragile molecules. They catalyze reactions on dust-grained surfaces. They play roles in forming amino acids, nucleobases, and the earliest chemical scaffolds of biology. If stars generate the precursors to these rings, then the universe becomes far more chemically fertile than once thought. It means that before planets formed, before oceans gathered, before atmospheres thickened, stars may have already been casting the sparks of organic chemistry across the galaxy. These molecules are more than survivors. They are cosmic scriptwriters, carrying the potential for life from one generation of stars to the next. Webb's discovery suggests a thrilling possibility. The chemistry of life may begin not in darkness, but in fire. If molecules alter energy transport inside stars, our models of fusion efficiency may need major revisions. Stellar physics has long been built on a clean separation. Fusion happens deep in the core, while chemistry, if it exists at all, belongs to the outermost layers or the space beyond. But Webb's discoveries blur that neat boundary. They suggest that even small pockets of molecular activity can ripple inward, affecting how heat flows, how pressure builds, and how efficiently energy travels from the core to the surface. And if those processes change, then the very engines of stars may not operate exactly as we thought. The standard model of stellar structure divides stars into clear zones: a fusion core, a radiative layer, a convective envelope, Energy generated in the core pushes outward, transported by radiation through dense regions and by convection through bubbling layers of rising and sinking plasma. For decades, this model has explained the brightness, temperature, and lifetime of stars with remarkable accuracy. But energy transport depends heavily on opacity, the degree to which matter absorbs or scatters light. And opacity depends on what that matter is made of. Molecules, even in tiny quantities, can dramatically increase opacity in certain wavelengths. They absorb infrared radiation with great efficiency, trapping heat in regions that would otherwise cool quickly. If these molecules cluster in specific layers, they may create subtle thermal bottlenecks, preventing energy from flowing smoothly. The consequences could cascade upward, altering the temperature gradient throughout the star. A steeper gradient leads to more vigorous convection. Stronger convection changes the mixing of elements, and altered mixing affects the fuel supply, reaching the fusion core. Even small shifts in these processes can influence how long a star burns, how brightly it shines, and how it evolves. This means that the presence of molecules, even in regions far above the core, might indirectly alter fusion efficiency. Some models suggest that molecular absorption could cool certain layers faster than expected. This cooling might reduce pressure locally, causing the star to contract slightly. A small contraction raises core temperature. A raised core temperature accelerates fusion. In this way, the existence of molecules in the outer atmosphere could subtly regulate the behavior of the core, pushing it into states we never accounted for. Other consequences extend to mass loss. If molecules help drive stellar winds by increasing opacity, then stars may lose mass faster. And mass loss dramatically influences fusion. A lighter star burns differently. It may transition to new fusion stages earlier. It may skip others entirely. Its death, whether gentle or explosive, depends heavily on how much mass it retains. In the most extreme cases, the molecular fingerprints Webb detects could even alter where and when a star switches from hydrogen to helium fusion, or how quickly it advances toward later stages like carbon or oxygen burning. Fusion pathways once considered fixed may now need to include variables tied to atmospheric chemistry. There is also the possibility of feedback loops. Molecules form in cool pockets. Molecules cool those pockets further. Cooling alters convection. Convection shifts energy flow. Energy flow shifts molecular formation. What emerges is not a static structure but a dynamic, self-adjusting system, one in which chemistry and fusion interact across vast temperature differences and unpredictable timescales. None of this suggests that fusion is fundamentally misunderstood. The core processes remain robust, but the environment above the core may be far more interactive, responsive, and chemically alive than models have accounted for. Webb is forcing physicists to confront the truth that stars are not simple thermonuclear spheres, but complex ecosystems where matter, motion, and chemistry all influence the fire within. And if molecules survive in these hidden layers, if they shape the flow of energy even slightly, then the textbook picture of how stars shine will need to be redrawn, line by line. A single class of molecules surviving in a stellar furnace could ripple outward, reshaping our understanding of stellar physics, chemistry, and cosmic evolution. At first glance, it seems absurd that something so small, fragile carbon chains, delicate dust precursors, microscopic silicate clusters, could wield such influence. But the universe is built on accumulations. Tiny changes layered over billions of years alter the destinies of stars, galaxies, and even the environments where life takes root. Webb's revelation of forbidden molecules inside stars is not a footnote. It is a tremor at the foundation of multiple scientific fields, one that forces us to reconsider how matter behaves in the harshest places the cosmos has to offer. The first and most immediate consequence is the challenge to stellar physics. Stars were assumed to be dominated by nuclear forces and plasma dynamics. Chemistry, we thought, simply didn't belong. But the presence of molecules inside stellar atmospheres means that stars are not chemically inert. They host intricate reactions that influence opacity, cooling, convection, and mass loss. These processes feed directly into how long a star lives, how it evolves, and how it dies. Even a small population of molecules can alter the temperature gradient in the outer layers, changing the efficiency with which energy moves upward. This means that the conventional models used to describe stellar evolution may need to be revised, expanded, or even rebuilt. The second consequence touches astrochemistry itself. If stars can foster molecules in high-temperature microclimates, then the universe has more chemical pathways than previously recognized. The diversity of molecules drifting through interstellar space may originate not only from cold clouds, but from the fiery, turbulent exhalations of living stars. This broadens the scope of where complex molecules and potentially organic precursors can form. Then comes the impact on dust formation. Dust is the backbone of planet building, yet its origins have always seemed a little too sparse to account for the immense quantities seen across galaxies. Now, with Webb suggesting that dust seeds may form deep inside stellar atmospheres, we gain a mechanism explaining how dust becomes so abundant. These seeds grow, drift into interstellar space, and help cool clouds where new stars and planets form. This single discovery may help close the gap in our understanding of how galaxies enrich themselves with solid material. Its consequences radiate even further into planetary science and the origins of life. If stars produce complex molecules, including precursors to aromatic rings, far earlier and far more efficiently than expected, then the building blocks of biology may have been circulating through the galaxy long before planets like Earth formed. Life's ingredients may be older, more widespread, and more deeply rooted in stellar processes than we ever imagined. Finally, this discovery alters how we look at cosmic history. If early stars hosted the same forbidden chemistry as modern ones, then the universe may have become chemically mature far sooner. Entire epochs of cosmic evolution may need to be reinterpreted through the lens of stellar molecular activity. One fragile molecule inside a star may seem insignificant, but it is a symbol, a quiet signal that the universe holds far more complexity than our models have dared to predict. Webb has revealed that inside the brightest furnaces of creation, tiny structures survive against all odds, rewriting the story of how stars breathe, how galaxies grow, and how the cosmos becomes capable of life. Every Webb observation hints that molecular complexity in stars might be common, an entire universe of forbidden chemistry waiting to be understood. What began as a curious anomaly, a faint spectral ripple in the light of a single star, has blossomed into a sweeping scientific revelation. Everywhere Webb looks, nearby red giants, distant blue supergiants, ancient stars in early galaxies, it finds echoes of the same delicate structures, the same fragile signatures, the same improbable chemistry carved into starlight. It is no longer a question of whether molecules survive in stars. The question now is how deep this mystery runs. For decades, scientists believed they understood the boundary between destruction and creation. Stars were the realm of fusion, while chemistry belonged to the cold void beyond. But as Webb peers deeper into the infrared, it reveals a cosmic truth far more intricate. Stars appear not as simple furnaces, but as layered worlds, zones of fury broken by fleeting pockets of calm, islands of shelter carved by turbulence, shock waves, magnetic fields, and the wandering paths of rising gas. Within those islands, molecules form, scatter, and leave their fingerprints on the escaping light. This discovery doesn't close a chapter, it opens one. The universe is not offering answers, it is asking better questions. How many types of molecules exist in these stellar microclimates? How complex can they become? Are aromatic rings forming in the folds of magnetic arches? Are dust seeds being built atom by atom in the shadow of shock-cooled gas? Do these chemical pockets influence the evolution of stars, or merely ride the currents of their changing atmospheres? And if this chemistry has been happening for billions of years, how much of the galaxy's dust, carbon, and organic material traces its origins to the trembling atmospheres of dying suns. Webb has only scratched the surface. Future observations will target stars at every stage of life, from newborn protostars choking on their birth dust, to bloated AGB giants shedding their final layers, to hypergiants on the brink of collapse. Each will carry a different chemical fingerprint, a different story written in its spectrum. Webb's deep field campaigns will probe ancient stars whose light began its journey when the Milky Way was still dustless, revealing whether this chemistry existed at the dawn of time. Even more tantalizing is what lies ahead. The next generation of models, ones that blend plasma physics with molecular chemistry, may reveal chemical pathways no human has imagined. Laboratory experiments, inspired by Webb's findings, will attempt to recreate molecular formation under extreme heat, and telescopes still on drawing boards may one day detect even more delicate signatures, revealing complexity beyond today's reach. We are witnessing the first hints of a universe that does not draw sharp boundaries between fire and chemistry, heat and structure, destruction and creation. Instead, it weaves them together, allowing complexity to flicker into existence in the most unexpected places. The mystery is vast, the story is unfinished, and with every new observation, Webb reminds us that the cosmos is not merely stranger than we imagine, it is stranger than we have yet learned how to imagine. The forbidden chemistry inside stars is not an anomaly, it is a frontier, and our journey into it has only just begun. As you settle deeper into rest, let the threads of our journey drift slowly through your thoughts. Tonight, we traveled into places no eye has ever seen, into the trembling atmospheres of distant stars, where shockwaves breathe, magnetic arches rise like luminous bridges, and fragile molecules cling to existence against all odds. We watched as Webb peeled back layers of fire to reveal a secret chemistry unfolding in moments so brief, yet so meaningful. They reshape our understanding of the cosmos. We learned that molecules, those tiny architects of dust, planets, and life, may be forming inside stars themselves. That the universe is not a place divided neatly between heat and cold, simplicity and complexity, but a vast tapestry woven from hidden microclimates and quiet instants of possibility. Even in the fiercest furnaces, the cosmos finds room for delicacy. Even in destruction, it leaves space for creation. And as you breathe gently now, remember that everything you are is part of this same story. The carbon in your cells, the iron in your blood, the dust beneath your feet, all of it began in places just like the ones we explored tonight, starry crucibles glowing across the darkness. You are connected to those ancient fires in every atom of your being. So rest with gratitude for the strange, beautiful universe that shaped you. Rest in the knowledge that you belong to something vast and ongoing, something that has been creating, refining, and discovering itself for billions of years. The cosmos is still writing its story, molecule by molecule, star by star, and you are one quiet, luminous part of that endless unfolding. Let the starlight fade gently behind your eyelids. Let the universe carry you. Sleep well,